Sinke har gjort en resa från Kamerun via Eskilstuna och hit upp till Sundsvall och en av våra egna masterstudenter som gjorde sin livsavhandling här för en liten tid sedan. Och Sinke är också ett exempel på att när det fungerar som bäst så kan ett universitet dra till sig kompetens från hela världen som då kan göra en stor nytta i lång tid. Och eftersom Sinke nu är nybliven stolt medlem i ett av våra jaktlag så tror vi att han kommer att vara kvar här inom överskådlig tid. Vi hoppas det i alla fall. So please welcome Sinke. You have your 15 minutes.
Yeah, thank you very much for the kind introduction. So my name is Sinke Henshaw Osong. I'm from Cameroon, as Olof said. Maybe I have to skip this slide, but I'm working on the peers group. So today is about innovation. So this is a definition that we want to transform the pulp and paper industry. So we try to bring creative ideas to produce new products or try to maintain the traditional materials there. So it's about creativity and success. And also this has been highlighted several times here. So it's about existing materials and new products there. And my research focus is to produce nanocellulose in this research area. And those are the fundamental questions that we ask ourselves. What is nanocellulose? Why do we produce it? And where is it coming from? And who are the actors? And all these kind of questions that we have to ask ourselves several times. And there are basically 3 types of nanocellulose. So we have bacterial nanocellulose, which is not from biomass, so I don't include it here. So I say there are 2 major types of nanocellulose. The spaghetti-like and the rice-like type. And we are going to deal so much with this, with this spaghetti-like. And we could see the images there from the NCC, which is a nanocrystalline cellulose, and the MFC, which is. And these are the very different kinds of mechanical treatment methods that we can use to produce this material. We can also use chemical-assisted method and also enzymatic method. And in my research project, then we are trying to use the high-pressure homogenization, and we could really see the different instruments used in this mechanical action. So we have the microfluidizer, homogenizer, different kind of aspect, and the tempo treatment is a very effective method of producing this. And this is just a picture to show what happened during the tempo treatment, and this is just the sodium hypochlorite that you use to bleach it after adding the sodium bromide and the tempo radical or the tempo catalyst, and you do the washing step in that. And this is a schematic view that you can see how we can produce this cellulose fiber material to nanocellulose. Either you pass through enzymatic method or the tempo, or you just do fractionation or pre-refining, and you do the mechanical treatment with high pressure. And we could also see an AFM image here showing the fiber structure or the fibrous structure, and this is a picture from Invensia, and this is a schematic picture also showing the process. In the process, we also try to use fractionation using the breed dynamic drainage jar to have fine material to treat. We could also try to heat this machine that we have at Mid-Sweden University, and that is the machine that we have there. It's a high-pressure homogenizer. It works around 600 bars, but due to process consistency, we maintain at 300 bars. So, and this is also the schematic picture of what happens inside the homogenizer. And we can also do some bleaching with TMP, and we use the SCA apparatus. They call the windmill refining. So we use different consistency, 150 gram pulp, and try to bleach it before we do the fractionation before treating this in the homogenizer as well. We can also use nanocellulose in paper making process using the rapid cutting sheet, and we use different blends to improve the strength properties. I'm not going to explain so detail here because of time. And from this image, we could really improve the Z strength of CTMP, and we use bleach craft pulp, but we could do this increment by also densifying the sheet, and this show good for CTMP, but not so good improvement in Z strength, but the sheet density was not that increased. Also, we are going to highlight a very fast method that we can use to evaluate particle size, and this is known as a CRILL. And this CRILL was developed by CRILL at STFI, and the method was now owned by PopEye, and it received this Wallenberg Award for signal analysis. So it's a very fast method to evaluate very tiny, hairy particles. So it's already used in the pulp and paper mill, and we wanted to evaluate nanocellulose using 1 gram dry solid content of this CRILL apparatus. Yeah. And we use the CRILL method with different homogenization time. We see that the CRILL value increases with increased homogenization time, and 20-minute homogenization time, we could really improve this CRILL value for both TMP and CTMP, but this picture showed the different temperature that was used in this method. So we could improve the CRILL value and try to characterize particle size of nanocellulose. We also use the peroxide sodium hydroxide pretreatment using the windmill refining and try to evaluate again with the CRILL. The scale is not the same here, but we could see that when we use 4%, we improve it more than 1%, and we try to check that as well. And these are images that I'm just going to flash. It's about the fraction that when you do fractionation, you see the bigger fibers. We do the fines. We have smaller fibers, parenchyma cells, showing, and they are same pictures. And we also treat the nanocellulose, but it's not in really nanoscale. We reduce the particle size. Yeah. The same for CTMP, and we also try to do the transmission electron microscope. Yeah, for CTMP, we really have, not the same as in nanoscale, but we reduce the size. Yeah, and because of lignin, we see like something like glue on this image. And also, I'm going to highlight the applications here. So, nanocellulose. High volume application in pulp and paper industry. We can use it also in cement factory, in automobiles, interior packaging materials, and also in plastic films and hygienic absorbent products. We can also use this in low volume streams, and this includes insulation material in paint architectura and also aerospace and also aerogel. And the last one, which is more to research novel and emerging materials. So we can use it in sensor technology, in water filtration, cosmetic, organolegs, photovoltaics, and also in photonic films. So there is great potential with nanocellulose. And these are the pictures here. So we can use it inside a car, in drilling of petroleum products to improve the rheology, in food dressing, pulp and paper industry, in cosmetics, and also tissue engineering, cement factory, flexible electronics, and also organic LEDs. We can read more on this in my thesis, and also I'm not going to conclude, but I give take-home messages that you people try to. The forest industry lies in our own hand, and this destiny, we have to try to change it also. There is need for collaboration and also real need of doing interdisciplinary research. There is need to go outside the box of research also, think outside the box. There is need for agility, and there is need, because we know that agility breeds innovation, so there is need for innovation in this pulp and paper industry. Now I go to what I'm going to do next in my PhD. So there is need to use NFC as strain additive in paper material. So, but from economical point of view, there is need to also substitute CMC, which is carboxymethylated cellulose, with our own traditional nanocellulose produced at Mid-Sweden University, known as NLC, to improve the Z strength in packaging material or in multi-layer applications. And our main idea is to use cationic starch and NLC to improve the Z strain in paper material. And also I try to show this future idea that we can use this research, not explain here. And I have to acknowledge the following people who organize this conference, and thank you. Oops, it's not coming. Oh. Yeah.
We have time for a few questions, and if I start, what's the main benefit with your way of creating nanomaterial compared to more traditional ones?
Yeah, idea in this project is that we don't have to use so much expensive chemicals or enzyme to use to produce this nanomaterial. And secondly, we don't want to use very good fibers to produce nanocellulose, so we try to take waste streams to produce nanocellulose and use it in large volume applications. So this can be implemented in the mill scale and also integrated to really improve the strength properties of this material.
So it's basically a cost-efficient, more cost-efficient way to create the material. Thank you very much. Have some other questions about this issue to Sinke? Well, thank you very much then, Sinke.